All right, so today, in today's lab, we're going to be talking about hypothesis testing. As always, like some of you might be further along with the process than others. I have just started teaching it today in my section, so we haven't covered T hypothesis testing, but we work through the the key parts of the structure anyways. So I'm going to start off the lab just by summarizing how a hypothesis test is going to work in terms of a process or in terms of the procedural approach. And then we'll start looking at examples of how we can use Rcmdr to help us through hypothesis tests. Okay, so we have, this is stat 151, X12L, lab 8 maybe, lab 8. And then we are November 3rd. Okay, so hypothesis tests. So a hypothesis test is a structured approach that we use to ask a question about a population mean in particular, but you could do it for any population value. The hypothesis test and the confidence interval are very closely related in that when you use the same sample of data and you use a common significance level, you can actually return the same result from both the interval and the test. So the assumptions of the hypothesis test and the assumptions of the confidence intervals will be the same. So in one case where we have simple random sample, normality, and then 3, we have sigma known. This is going to lead us down the path of a Z-score for the test statistics. So we're going to have, like with the confidence interval, we could either do it based off a Z-score or a t-value. With the hypothesis test, we can either do it based off the Z-score or the t-value. Okay, so if our other set of assumptions are SRS, normality, but we do not have sigma, then this is going to lead us down the path of the t-value. All right, when I teach hypothesis tests, I do it using a 6-step approach. So on the first step, we have to declare H0 and HA. So we can have 3 different declarations here. We can have H0 mu equals some value versus HA mu different from some value. We can have H0 mu equal to some value versus HA mu is greater than some value. And then we can have mu equals some value versus HA mu is less than some value. Okay, so these are the 3 different hypotheses that we could declare, and the choice of the alternative depends on the structure of the question. So basically, you'll notice that we have equality in all of the H0s. The H0s are called the null hypothesis. So that's consistent for every type of test. And then in HA, which is the alternative hypothesis, we have one of 3 possibilities: not equal to, greater than, or less than. And the sign, so the not equal to sign, the greater than sign, or the less than sign, that depends on what we are being asked to find in the question. Okay. On the second step, we state the significance level. Which is alpha. That's given to us in the problem. On the third step, we compute the test statistic. Which is, in this case, z equals x bar minus mu 0 over sigma divided by the square root of n. So we're using a z-score here because we have sigma in the third assumption. So like with the confidence intervals, when sigma is known, it's a z-score. When sigma is unknown, it's a t-value. On the fourth step, we take one of 2 approaches. So we compute critical values / the rejection region, or we find the p-value. Okay, so we have two options for the fourth step. We either find our critical values and then the corresponding rejection region, or we find the p-values. Again, hopefully at this point, if you're in the lab today, you've seen the definitions of these already. I'm not going to spend a lot of time going over this right now because it is something that you should see in detail in lecture. And the goal of our lab is just to use Rcmdr to conduct the test. But as we work through the illustrations, if you have questions about where I'm getting certain values, please let me know, and then we can come back to reference this step, because this will probably be the step of concern. Okay, so on step 5, we make a decision about H0, and then on step 6, we conclude. All right, now, if we go down the other path, which is the t-value path, all of these steps are exactly the same except for step 3, where we would have, oh, it sucks. Okay. So all of these steps will be exactly the same except for step 3, where we would replace the z-score with the t-value. So here we would have the following. So we would have our assumptions, and then we would take all of this information here. It's going to be exactly the same, except that step 3 is going to have a p-value rather than, or is going to be a t-value rather than a z-score. So here we can just simply replace this like this. Okay. So basically the goal of today's lab in summary is just to work through the steps of the hypothesis test. Okay, so we're gonna look at examples of how to structure the null and the alternative. Again, hopefully you've already seen some illustrations of this, so you're building some familiarity with the language. We're just gonna be basically doing the same thing here. But where Rcmdr is really gonna come into play is we're gonna learn how to use Rcmdr to directly get our test statistic and our p-value. And we're also gonna kind of take like a brute force approach like we did with the confidence interval, where we basically do all of the steps by hand, but we can find the p-value directly using Rcmdr. Okay, so again, today's lab is focused on conducting hypothesis tests using Rcmdr, or using Rcmdr to aid us in working through a hypothesis test. Any questions? Oh, sorry, wrong button there. All right. Okay, so let's set up our demo questions. All right. So last class, we actually worked through a lot of these questions, and the confidence interval questions and the hypothesis testing questions are intertwined with each other. So we're going to be reviewing or looking over some of the problems that we talked about last class. So number 16 will be the first one we start with. So as a reminder here, we have a random sample of 1,280 students taken from a larger population mean, or is taken from a population. So our sample size is 1,280. Their average student loan is equal to $18,900. Suppose it is known that the standard deviation is $40,222. The first thing that they ask us to do is find a confidence interval. So this is what we talked about last class. What we need here is this information. Okay, so we can use this information to conduct a hypothesis test as well. So if we scroll down to 16H. In 16H, we have perform a hypothesis test to determine if there is evidence that the population mean for student loans differs from $20,000. Use a significance level of 10%. Okay, so in the table below here, you can see that the steps of the hypothesis test are more or less summarized for us. So here in the first box, we have our hypotheses. So what we would have here is H0 mu, this little mu here, mu equals 20,000, okay, versus the alternative that H0 mu is not equal to 20,000. Okay? And the reason that we have not equals to is because in question H, the language here says determine if there is evidence that student mean loans differs from 20,000, right? So if we were to highlight this passage here and then boldface this word differs, this is the language that we need to look out for when structuring our alternative. So the question is asking us to test for a difference of mu versus 20,000. So that's why we have the does not equal sign in the alternative. So now I just need to find the does not equal sign. Should be you think it, oh, it's right there. Duh. Yeah. Right. So any questions about that first point, right? So we're just setting up the test. This would be step one as I kind of laid it out before. Okay. So now we're being asked to declare X bar. So X bar is equal to the value given to us at the top of the problem here. So in 16, it tells us the average of the 1,280 students is 18,900. Okay. So our X bar for this particular problem is going to be 18,900. Okay, now we're being asked to compute the Z-score. So we're gonna have, in this case, if we take this little thing and copy and paste it, so we're gonna have X bar is 18,900 minus mu, which is 20,000, divided by sigma, which we're told in the question is 40,222 over little n, which is 1,280. Okay, and then in working out this equation here, can I get this all into one line? Yes, there we go. I should end up with a value of negative 0.97844 roughly. Okay, and if we wanted to, we could actually work this out in Rcmdr. So if we open up our R page, oh, computer's freaking out. We open up R, we open up Rcmdr. Go. Okay. Right up here, in the script, we could type 18900 minus 20,000 divided by 40222 divided by the square root of 1280. And then we can submit this, and there's the value given on the slide. So we can take this value and we'll just stick it in. Okay. So the next thing that we need to do is work out the values of the critical region and the p-value for the problem. Now, what we have done so far is we have worked through step 1 and we have worked through step 3 as I outlined them. We haven't stated the significance level yet, but you can see here that we have a little box for significance level here. So in this box, we can type 0.10 because that is the significance level for the particular test that is of interest. Okay, now the p-value for this test is going to be 2 times the probability that x bar is greater than 18900. Actually, you know what? I don't like the way that this is structured. I'm going to do this slightly differently. Okay, so if we take our p-value approach, we're going to have the following setup. We're conducting a two-tailed test. So that means that our p-value is going to be equal to the probability that z is greater than 0.9784 plus the probability z is less than negative 0.9784. Now, the reason that we have z being greater than the positive and z being less than the negative of the same value is because it is a two-tailed test. So this addition here represents the two-tailed feature given in the alternative. So the does not equal sign in the alternative leads to the two-tailed test, which is why we're adding the two areas above and below the test statistic. Now, because the curve is symmetric, then we can say that this is simply the probability this is 2 times the probability z is greater than 0.9784, which is equivalent to 2 times the probability z is less than 0.97 or negative 0.9784. Okay, now, typically, to solve this type of problem, we would have to go to the z table, but we don't have to do that here because we are working with the Rcmdr. So from Rcmdr, we're actually able to work out the p-value directly. So to do this, we're going to look up either the probability of being less than negative 0.9784, or we could look up the probability of being greater than positive 0.9784. And in each case, we can just multiply by 2. So we're going to click distributions, continuous, normal probabilities. Here, we're going to type negative 0.9784. We're going to do the lower tail because it's already set up for us. We'll click OK. And then we end up with 0.1639383. So then we'll have 2 times 0.1986, 2 times 0.1639383, which gives us 0.3279. Or let's write it out fully, 8574. So then we could say that the p-value for this test is 0.328. Okay, so what we have covered here again are declaring the hypotheses. So we have step 1 of the test of the procedure. We computed our test statistic, which would be step 3 of the way I structure it. And then we computed the p-value. In the next box, we are comparing the p-value to the significance level. So our p-value is 0.328, which is greater than 0.10. Therefore, we do not reject alpha, or we do not reject the null hypothesis because the p-value is greater than alpha. So as a reminder here, oh, sorry, I don't want that. Okay. So as a reminder here, the rules are if p-value less than alpha, or sorry, greater than alpha, do not reject H0, otherwise reject H0. Okay. So in this situation, so the rule for a p-value is always the same. If it is bigger than alpha, you do not reject. Otherwise, you reject. In this situation, we're not going to reject. That's why I have bold-faced do not reject, because our p-value, which is 0.328, is bigger than the significance level of 0.1. So then we can say, at the 10% significance level, there is not significant evidence that the average population differs from 20,000. So the conclusion that we are writing for the test, this would be step 6, is in terms of the alternative. So here what we are saying is that there is no evidence that the average population differs from $20,000, which is what we were testing the null against. Okay, so this illustration is of how to take the p-value approach to complete a hypothesis test. So step 4 here, we use the p-value rather than a critical value to work through the components of the test. Okay, does anyone have any questions at this point about any of the process? In this situation, Rcmdr was used to find Z and the p-value. Okay, so I used Z here manually, and then I used distributions, continuous, normal probabilities to find the p-value of the test. But I'll show you how to do the full test as well. Okay. Question 17, the same idea here, except that now we have sample standard deviation rather than population standard deviation. So if we work through 17 and we go down to part H, in part H we have perform a hypothesis test to determine if there is evidence that the population mean for student loans differs from 20,000. So in 17H, we're doing the same thing that we had just done in 16H, except that we no longer have sigma. Okay, so now what will happen is our test statistic will be a t-value, and the p-value that we find for the test will be found using the student t-curve rather than using the normal curve. So here, for H0 and HA, we're going to have this exact same null and alternative. Okay, so we can come back up here. We can just copy and paste this. It does not change because we are asking the same question, just using slightly different information. Our t-value, which will be computed on step 3, is also going to be very similar to what we had in H. The difference here is just that we're using the t-value rather than the z-score, and so sigma, which was 40,222, is now going to be replaced by the sample standard deviation, which is 45,192. All right, and in working this value out, we should end up with a number quite close to what we had before, which in this case is 8708355. Okay, and since we're using a t-value, we can also note our degrees of freedom, which is n-1 here, which is equal to 1219. Okay, so we're still performing a two-tailed test. So the p-value for this test is going to have the exact same structure that we had above. The only difference is that we're going to be replacing our z-score, the capital Z, with a capital T in this case, because we're using a t-value rather than a z-score. So here we're going to have, because it's a two-tailed test, we'll have t is greater than 8708 plus the probability that t is less than the negative, which will give us 2 times the probability that t exceeds 0.8708, which is the same thing as the probability that t is less than 8708. And now what we can do is we can use Rcmdr to find the exact p-value based off the student t distribution. Oh, because I can't subtract. Thanks, Taylor. So to do this, we would go to Rcmdr. We would click distributions, continuous, t distribution, t probability. So we're doing the same thing, we're just working with a different distribution. Our test statistic in this case, we can just use the negative. And our degrees of freedom is 1,279. So we're finding the probability of being less than the test statistic value on 1,279, which gives us 0.1920037. So we multiply this value by 2, and we end up with 0.3840074. Okay, now the rules for using the p-value are exactly the same. So we can mark down that our p-value is 0.384. Our significance level is now 0.05. Notice in the question that we have use a significance level of 5%, so we've made a slight change to the significance level here. This is still greater than that value. So because our p-value is bigger than alpha, we do not reject H0. So then we can say at the 5% significance level, there is not significant evidence that the average population student loan differs from $20,000. So in 16H and 17H, we did the same thing, the same process, we followed the same steps. The only difference was in 17, we had sample information. Specifically, we had the sample standard deviation, and we did not have the population standard deviation, which meant that the test statistic had to be a p-value in order to, or the test statistic now is a t-value rather than a z-score. All right, so once we found our test statistic, we then had to find the p-value. The p-value we can find using Rcmdr directly. Typically, p-values in lecture would be found using the standard normal table or the student t table. Yeah, so to find 0.1920037, this value here is the probability that t is less than negative 0.8708. So I went to Rcmdr and I clicked distributions, continuous, t, t probabilities. Then I selected negative, then I put the test statistic value in for variable, the degree of freedom. I'm using the negative here, so I clicked lower tail. If you wanted to, you could use the positive and click upper tail. That would work as well. Okay, and that's where the 0.1920037 came from. Okay. So again, we work through, it's the same general process. The big difference is just the distribution of the test statistic. So when sigma is known, we're using a z-score, so we would use the standard normal curve. When sigma is unknown, we're using a t-value, so we would use the student t-curve. In these two illustrations, Rcmdr was used strictly to find p-values based off of the test statistic. In the next illustration, what we will see is how we can use Rcmdr to perform a hypothesis test directly. So the same way that we could use Rcmdr to build a confidence interval for us, we can use it to perform a hypothesis test for us as well. All right, in question 18, we're working with the data set doctor exercise demo. In question number, or in part E of this question, we're asked to perform a hypothesis test to determine if there's evidence that the average weekly minutes of exercise for the Canadian doctors has changed from 281. So to set this up, we have the following. Mu equals 281, and then we have mu not equal to 281. Now, the reason that we have not equal to 281 is because of the language given in the question. So it says, perform a hypothesis test to determine if there is evidence that average weekly minutes of exercise has changed. Okay. So it's this word here that's indicating general difference. When you're asked if something has changed from a particular value, you can be bigger than that value or less than that value. So therefore, we would be doing a two-tailed test in this case. So that's why we have the does not equal sign in the alternative. Now, if we go back to the beginning of question 18, and we look at some of the information that's given here, we only have the sample. So the data that we are working with, the description of the data does not include any population information. So we do not have sigma here. We will only have sample information. So to construct the hypothesis test using Rcmdr, we would go to Rcmdr, and the first thing we have to do is import the data. So data import from Excel. This is going to be the doctor data. Right? And now we have to locate the data on our machine. And here it is. Okay, so if we view this data set, we can see that we have our 20 observations. We don't have any population information, so we only have sample values. So what we would do here, the first thing that we would do is we would click statistics, summaries, numerical summaries, and then we can look at the standard deviation and the mean of those numerical summaries. All right, if we wanted to perform this question by hand, so sort of take the brute force approach like we looked at before, we would then be taking this number and plugging it into the formula directly. So we would have t is equal to x bar minus mu 0 divided by s over the square root of n. And then we would be pulling the numbers that we need from the summary and then working through the steps directly. However, because we have Rcmdr available to us, instead of doing that, what we can do is have Rcmdr summarize all of the results of the test for us, and then we can just pick apart the output. So if we click statistics, means single sample t-test. So again, that's statistics means single sample t-test. The same commands we use for the interval. We would choose our variable, which is exercise minutes. We would choose our hypothesis. Now remember that we are doing a two-sided test because the language has asked if the minutes has changed from 281. So we have a two-sided test clicked here. The null hypothesis is mu is equal to 281. Okay, so I've changed my value to 281 here. And then we also have the confidence level shown below. In this case, it doesn't really matter what you put in for confidence level, but I'll change it to 0.90 to be consistent with the language, which says use a significance level of 10%. So if the significance level is 10%, the confidence level would then have to be 90%, which is 0.9. Okay. Any questions before I click OK here? Okay, so here's the output from the test. Let's take this over to the Word doc so that we can take a look at it. All right, so let's break apart this output using a similar table to what we were using before. So first off, you can see that it has the data name and then it has T, degrees of freedom, and p-value. So the T here is our test statistic. Okay, so that is what we calculated by hand in the previous question. So this value here, 1.9231, is found by taking x bar, subtracting the hypothesized mean, and dividing by s over the square root of n. You can see that it gives us the degrees of freedom for the test, which is 19, and then it directly gives us the p-value for the test, which is 0.06959. Okay, so we have a p-value for the two-tailed test. You'll notice here it confirms the alternative is that the true mean is not equal to 281, which is what we have here. So we have confirmation that we selected the right alternative. Now all we have to do is compare our p-value to the significance level. In this case, 0.07 is less than 0.1. So we can reject the null hypothesis, and then we can say at the 5% significance level, there is evidence that the average weekly minutes of exercise for Canadian doctors has changed from 281 minutes. Yes, good catch. So you can see in the case of hypothesis testing and confidence interval construction, Rcmdr makes it quite easy. It's really, once the data set's loaded, it's just a click away from actually having the results of the test. All right. I want to mention that the assumptions here are the exact same assumptions that we use for the confidence interval. So all of the previous work that we did last week for checking assumptions of the interval, we would also do that here for checking the assumptions of the hypothesis test. So that would be the exact same structure from before. Okay, let's see what we have below. So in question 19, we're talking about Alan's midterm data again. So last week we checked all this stuff out. Okay, so here we have Perform a hypothesis test to determine if there is evidence that the true average score of all calculus students taking the midterm differs from 49.5. Okay, so we go to Rcmdr. We're going to import our data. So this will be the Allen data. Right. Okay, so we want to conduct a hypothesis test to determine if the true mean differs from 49.5. So we're going to have 49.5 in our alternative, and then in the null, and then in the alternative, we are going to have mu different from 49.5. Okay, so here's my... All right, now, so setting this up in R is going to be done in the exact same way that it was done before. So we have Allen's data. We're going to click statistics, means, single sample t-test. We're going to select the midterm mark as our variable. We have a does not equal sign as the alternative because it's a two-tailed test. The null here is going to be 49.5. And we are testing at the 1% significance level. So our confidence interval would be set to 0.99. Okay. Any questions on the setup before I click OK? I feel very robotic today. You click here and then get this, and then use this to get this. Click OK. Here's our output. All right, so from the output, we have our t-value, the degrees of freedom, and we have our p-value. Okay, so our p-value is 0.03, which is greater than alpha, which is 0.01. So we do not reject H naught. And then at the 1% level, we can say that there is not evidence that average grade on Allen's midterm differs from 49.5. Any questions on that? The degrees of freedom, I mean, to be honest with you, in the context, with the way that we're doing the hypothesis test, it's not really telling us anything outside of just the sample size -1. So in this case, it's 19 because we have n minus 1. So that's kind of just telling us that the sample size is 20 in this case. If we were finding the p-value manually, like we did in the exercises at the start of the lab, then we would need the degrees of freedom to find that p-value. But in this case, it spits it out for us. So it's sort of just extra information, really. The most critical part of the output is the p-value. All right. Okay, fill in the following. A 1 minus alpha % confidence interval will always give something decision as a something test of significance. What the hell does that mean? So we have here, oh, I see. Okay, so this will always give the same decision as an, in this case, alpha % test of significance. So the idea here is simply that as I had mentioned before, the assumptions of the hypothesis test and the confidence interval are the same, right? So it actually turns out that when we conduct a hypothesis test at a certain significance level, so 5%, the corresponding confidence interval, which is constructed at the 1 minus 0.05% level, will give the same result. So the interval in the test will always give the same conclusion. And that's what this statement is reflecting. Perform a hypothesis test to determine significant evidence that the true average score of all calculus students taking the midterm is more than 50. Okay, so here we have a little bit of diversity in the question. Thank you. A little bit of diversity in the question. So we have perform a test to determine if the true average score of all calculus students is more than 50. So now we have some direction to work with. So here we'll have equals 50, and here we'll have greater than 50. So now we're working in under a different part of the curve. We're working with a different type of test. So the language more than 50 indicates mu being bigger than 50. So in Rcmdr, we're working with the same set of data. So we're going to click statistics, means, single sample t-test. Now what we'll do is we'll select the last option, population mean being greater than mu naught. We'll change this to 50, and we'll change the corresponding confidence level to 0.95. Any questions before I continue? All right, so we click OK here. Here's our output. All right, so again, our t value is 2.0178. We have 19 degrees of freedom. Our p value is 0.0289. So that means that here we can write the p value is 0.03, which is less than alpha, which is 0.05. So in that case, we can reject the null since the p value is less than alpha. So at the 5% level, there is evidence that the true score is more than 50. Any questions? All right. Okay, so same idea here. Perform a hypothesis test to determine if there's evidence that the true average score of all students is less than 54. So here we have true average score less than 54. So we go to Rcmdr, statistics, means, single sample t-test. Here we have midterm. We select our less than option. Here we plug in 54. We have a significance level of 0.5. Okay, so we have the following. Okay, so here we have mu equals 54, mu less than 54. Our t value is negative 1.2632. Our degrees of freedom is 19 again. And our p value is 0.1109. Okay, so here we have 0.111, which is greater than the significance level of 0.05. So in this case, we do not reject since the p value is bigger than alpha. And then we can say there is not significant evidence in this case. Cool. Any questions so far? So there's one more exercise we can work through if you guys want. I'll leave it up to you. I'm happy to work through it. Otherwise, I can just use the rest of the time to answer any questions you might have. Does anyone have a preference? Yes, please, to which? Okay. So we're going to work with the hours, home, work, gender data. So I just need to download this onto my computer. So bear with me for a moment here. I'll actually just pause the Zoom. So the question on the table was, say on a test, one of the assumptions was not met. Would we just write that and then not complete the question? In the context of a testing situation, I would complete the question. But in the conclusion at the end, you would have to make a note of the fact that assumption was not met. So say, for example, the normality assumption wasn't met. At the end of the test, I would write something to the effect of, if the normality assumption can be verified through a different means, then at the 5% significance level, there is evidence, blah, blah, blah. So I would just sort of make a condition on the conclusion that that assumption needs to be verified somehow. Otherwise, the result should not be trusted. Does that make sense? I wouldn't, in practice, if the assumptions aren't met, then I would stop the procedure. But on a test, I would complete it because you probably will lose marks in a testing situation. Okay, so we are now working with this hours, home, work, gender data. So I've loaded this in here. Okay, let's see. Oh, okay. Oh, it didn't work. File may be corrupt. Let's try this again. Huh. Okay, there we go. That was weird. All right, so here is the data set that we are now working with. So we have this hours, it's called the, oh, sorry, let me show you the word. So it's this hours, homework, gender. Okay, so this file contains weekly hours of homework per classroom hour for 2 independent random samples of students. Output is provided below. Students should verify that they can produce it. Okay, is there significant evidence that female did more than 2.8 hours of homework per classroom hour on average? Okay, so what we are interested in here is determining if mu for the female gender is equal to 2.8 versus the alternative that mu is greater than 2.8. So if we look at the language of the question, it says, is there evidence that females did more than 2.8 hours? So right off the bat, we're given what we are interested in testing. So we want to know if females do more than 2.8 hours of homework per classroom hour on average. All right, so if we go back to Rcmdr, we are interested in the female gender, and then we're going to want the first variable for the female gender here. Okay, so we're going to do a single sample t-test. Can I apply the condition? All right, I need to see. Okay, so it says, let's need to view this again. The reason that I'm just hesitating here a little bit is because I just want to make sure I select the right category. Okay, I see how this is working. So if we look at the data, you'll see you have female and then you have male here. And then the way that they split the data set up is they took the entries for the female group here, and they put it into this column. And then they took the entries for the male group here, and they put it into this column. The reason that the data is structured this way is because then we can just select that column directly in the single sample t-test command, and we don't have to worry about partitioning based off of the first group. So we're gonna have statistics, means, single sample, HHF in this case. Okay, so we wanna know if the population mean exceeds 2.8 here. So you'll see I've selected the variable. I have a directional test greater than. I have a mu equals to 2.8. And then the significance level is 5%, so I can leave that as 0.95. Okay, so I click OK. I'm gonna get the following. All right, so here I have t equals 1.8924. I have a degrees of freedom of 34. My p-value statement here, okay, so this is going to be p that t is greater than 1.8924. And then the p-value from the test is 0.03349. Okay, I'll just round that because of space issues. So notice here that our statement, so I have p, t is greater than, that symbol here is because of the symbol in the alternative. So our p-value direction is mimicking the alternative direction. Okay, so I have 0.03. We have a significance level of 0.05. This is less than 0.05, so we can reject. So then we can say at the 5% significance level, there is significant evidence that females, that on average, female identifying McEwen students do more than 2.8 hours of homework per class hour. Part B, is there significant evidence females did a differing amount of work? Okay, so this is actually a very similar question. The only difference here, so you'll see the language is kind of setting us up. So instead of having more than, we have a differing amount. So what does that mean? It just means that in our statement here, let me just pull this up a bit. In our statement here, this symbol is now going to be replaced with the does not equal sign. Okay. So when we go back to Rcmdr, we'll click statistics, means, single sample t-test, HHF. We're going to change this only to does not equal. Same significance level, same values of interest. We're just changing our alternative to a two-tailed. That gives us the following. Okay, so this is actually very interesting because if we look at the output here, what we can see is that the test statistic is exactly the same as it was above, right? So we had 1.8924 above. The degrees of freedom is obviously the same. Now the p-value statement is going to be 2 times because of the does not equal sign. So now we're multiplying by 2 here, greater than 1.892. Okay, and then you can see here we have 6698, which if we round it is going to give us 670. Okay, that is exactly twice the p-value given for the directional test. So by changing to a two-tailed test, the only difference is the p-value has now doubled. But everything else, the test statistic and degrees of freedom is exactly the same because the sample hasn't changed. So the direction of the alternative has changed the p-value, but it has not changed anything else because the sample is still the same. So in the two-tailed test case, we now have a different result, which states that we do not reject because the p-value here is greater than what was given above. It's a terrible sentence. Okay, so any questions on that? Okay, C. Is there significant evidence females did less than 3.6 hours? Okay, so this is a very similar question again. So here we're gonna have mu equals 3.6 versus the alternative mu less than 3.6 now, right? So the question is asking us right off the bat, significant evidence they did less than. So our T, so in R, we would go statistics, means, single sample t-test, same variable. We're now a less than situation. This is now 3.6 instead of 2.8. And we're at the same confidence level. So we click OK. All right, so here we have our T value, which is negative 2.34. We have our degrees of freedom, which is still 34. Our P value is going to be PT less than negative 2.35. And then the P value is going to be 0.012 in this case. Okay, so we have 0.012, which is less than 0.05. So we can reject the null, and then we can say at the 5% significance level, there is significant evidence that on average, female identifying McCuding students do less than 3.6 hours of homework per classroom hour. All right, so those are the hypothesis testing questions. Let's finish off this question because we have a bit of time. So in part D, it says, state the 95% confidence interval for the amount of homework done by females. Does this confidence interval provide significant evidence that the female students do an average amount of homework that differs from 3.6? Okay, so we would click statistics, means, single sample t-test, HHF, population mean 0, we'll set this to 0, and then we have a confidence level of 95. So we're not interested in the hypothesis test, we're only interested in the confidence interval right now. Okay, so we take our data. Again, here you'll see that I have a 0 in the alternative because I'm not interested in testing any value directly. So here's my 95% interval. And now it says, does the interval provide evidence that the female students do an average amount of work that differs from 3.6? In this case, we would say, yes, it does. And the reason is, if we look at the interval, we can see that the interval covers 2.7 or 2.77 to 3.54. 3.6 is outside of that interval, which means that the interval is suggesting that the true mean is somewhere between 2.77 and 3.54. which does not include 3.6. So we would say here, since 3.6 is not within the confidence interval, we have significant evidence that the average amount of work differs for female students. All right. Any questions about that? Okay, and then here, it says highlight the answers. In part A, the test is, okay, so in part A, we have a greater than sign in the alternative. So part A is the right-sided test, where right means positive or upper tail. Part B is the two-tailed test, because we have a does not equal sign in the alternative here. The p-value in part A is half the value, the same as or twice the value of the p-value in part B. Okay, so the p-value in part B is going to be twice the value. No, sorry, the p-value in part A is going to be half the value of the p-value in part B, because the p-value in part A is a single-sided test based off of the same sample of information as the two-sided test in part B, which means that it's half the size of the two-tailed p-value. Our decision in part A is different from our decision in part B. And that's just because the p-value exceeded alpha for the two-tailed test, but was less than alpha for the one-tailed test. All right, so that is all of the hypothesis testing examples that would be relevant to us for the from the demo sets. So there's still about 10 minutes left here. I'm gonna stop the recording because this is the point where the actual lecturing material is over. But I'll stick around for the next 12 minutes if anyone has any questions. And otherwise, have a good couple of days, and I'll see you guys for lab next week. And if you have lecture with me, then I'll see you in lecture this afternoon or on Thursday.